In this class we are going to talk about general relativity, which is a theory of gravity proposed by Albert Einstein in 1915, 10 years after his proposal of a special relativity. Several years before producing the theory of general relativity, he came up and used a principle that we are going to use, as he did, in order to derive many of the consequences of general relativity. And this is the principle of equivalence. And this is principle of equivalence between gravity and a constant acceleration. So as you know, the acceleration produced by gravity is independent of the mass of a body. Namely, if you put in a particular location a body of any mass, because the gravitational force is proportional to the mass, and F equal to ma, mass times acceleration, also contains the mass in the other term of Newton's second law, then the mass of the object drops out and the acceleration is the same independently of the mass of the body. This was already discovered by Galileo Galilei, and he called it the law of falling bodies. And he discovered that close to Earth. He said on Earth all bodies fall with the same acceleration due to gravity independently of their mass. But actually this is true everywhere. So Einstein had a thought that actually he called the happiest thought of his life. And he said, well, gravity, the strength of gravity depends on the observer. So he thought of the following Gedanken experiment, thought experiment. Somebody jumping from a roof would be in free fall, and if he or she leaves something like a piece of chalk while he or she is in free fall, the chalk will also be in free fall, and therefore it would be hovering in front of the person. So in the brief moment before reaching the floor, this person could think that there is no gravity. And actually we have an example of people in free fall in the astronauts. The astronauts that are orbiting around the Earth are in free fall. They are falling towards Earth, but always missing Earth because they move very fast. They are in free fall together with everything else in their spaceship, and therefore they are floating as if there would be no gravity. Now this is exemplified. We're going to see a demonstration that we fittingly call the Einstein Elevator, and consists of a cage in which one can throw out a projectile. So a ball is expelled at a certain velocity. So if the cage is at rest with respect to us on Earth, then the path of this projectile with respect to the cage is the parabolic path that we have seen due to the acceleration of Earth downwards. So how come we can see that this path is parabolic? It deviates from a straight path because there is a sheet of plastic with a hole. And when the cage is at rest, the particle, the projectile, does not pass through the hole. Instead, if the cage is in free fall, at the same moment the projectile is in free fall, then both cage and projectile are falling with the same acceleration, and the path of the projectile then is a straight path with respect to the cage. It goes through the hole, and it can be collected to the other side in a little net that is on the other side. And so a straight path is what we expect if there are no forces. So the projectile path with respect to the cage is as if there would be no gravitational forces whatsoever. And so now we are going to see the demonstration shown by Martin Simon.
This is called Einstein's Elevator, and it's to demonstrate the equivalence between a gravitational field and an acceleration. We have two guns here and here that are aimed in a straight line trajectory to the capture bags over here. And the bullet can only get into those bags if it follows a straight line trajectory from the standpoint of the elevator, somebody inside the elevator. Otherwise, there's a barrier here which will prevent the balls from reaching the capture bags. We can demonstrate that by firing the guns now at rest and see what the effect is. You can see that the balls both hit the barrier because they were falling under the influence of gravity following a parabola. Okay, we've rearmed the guns, put the bullets in. We've set the cage so it can go into free fall. When it's free falling, there's a switch that will trigger the bullets to be fired from the guns. And we'll see what happens this time. 3, 2, 1.
So, as we have just seen, the principle of equivalence is a realization of this idea. So if somebody is hovering seemingly without gravity, it could be that here we see an Einstein is weightless because this spaceship is in the middle of nowhere where gravity is negligible, or the situation from the point of view of the person inside this spaceship is indistinguishable if the person with everything else is in free fall due to whatever gravitational forces are there. So this is the principle of equivalence, right? Free fall and acceleration, constant acceleration, allows to eliminate the acceleration of gravity, and so we are in a situation indistinguishable from having no gravity at all. On the other hand, assume that we are in the middle of nowhere in a spaceship that is being accelerated upwards. Then in this situation, the force that has to be given to the person and everything else upwards in order to produce an acceleration, let us say equal to g, will push everybody up, and so the situation would be indistinguishable if the person is at rest on the surface of a planet like ours, for example, or is just accelerated upwards in the middle of nowhere, since everything would be accelerated in the same fashion. So this is what the principle of equivalence says. So now we are going to draw several conclusions that apply to the situation on the right. So an accelerated spaceship or elevator upwards, and we will apply it to the situation of being on Earth or in the presence of a planet, for example, or large mass. So here it is in the bottom of this page that actually this lady who is in the spaceship could not see the difference between having an accelerated upwards spaceship or being in the surface of the Earth. So from us seeing it from outside, maybe we can distinguish that actually, since there are no forces of gravity in this example, when she lifts this balls that she had in her hand, the balls stay there hovering, but the bottom of this spaceship is coming in an accelerated fashion towards the balls. So from the point of view of this lady, she cannot distinguish if they are the balls that are approaching the bottom of the spaceship in an accelerated fashion because she is on the surface of the Earth and the balls are accelerated, or if the balls stay there and it is the bottom of the spaceship, that actually the floor of this elevator or spaceship, that are approaching the balls. So for an observer accelerated upwards, the body falls just if it would be on Earth. So we can extend then this analogy to other situations. Imagine again that we are in this accelerated vessel moving upwards, and we throw a ball horizontally. So the ball would just go straight, in a straight manner, a straight path. But since the vessel is accelerating upwards, the floor will approach in an accelerated fashion the ball, and therefore we will see the ball as making the parabolic path that is characteristic of projectiles on Earth. Yes, but what is useful about this way of thinking? Well, this way of thinking tells us that if we throw light horizontally instead of throwing a ball, then light will move straight, right, from side to side. However, since the elevator or the spaceship is accelerating upwards, the ray of light will approach the bottom, the floor of this spaceship in an accelerated fashion, in the same way the projectile did. Therefore, applying the same, so since this situation is indistinguishable to the presence on Earth or in any other place where there is gravity, we conclude that light also drops. Namely, light is deflected when passing near a mass as a pebble would, in the same way, except for the fact that light moves at much larger speeds, and therefore we see the deflection less. However, gravitational lensing, which is a consequence of light being deflected by the presence of mass, has been observed. Here you have, for example, a distant quasar, a very bright source, very far away, and the rays of light that should move straight are actually deflected by the presence, in this case, of a cluster of galaxies. And then you see multiple images arriving to us. Here you see multiple images of one particular quasar taken with the space telescope, the Hubble Space Telescope. Here you have another example. If the lensing object is just in the middle, intervening between the observer and the object whose light is being lensed, then the lensing happens all around in the same manner, and there will be a ring formed that is called Einstein ring. And here you see pictures taken of several Einstein rings. So these are images, modern images taken with modern telescopes, but actually gravitational lensing was what was used to prove the theory of relativity. So it was first observed during a total sun eclipse in 1919, and what was observed was the gravitational lensing or deflection of light due to the presence of the sun of stars that were near the sun. So as you see, the apparent position of the star moves upwards with respect to the sun, because the light is deflected. The angle was very small, and this could only be seen for light that passing very close to the sun, so one needed an eclipse. But in 1919, this was used as a confirmation. Now, although we can understand the effect using the equivalence principle, general relativity goes a bit farther. In the general relativistic explanation, it's actually that the presence of a mass, such as that of a star or a planet, etc., deforms space-time. And so it is the deformation of space-time that deforms or actually bends the path of particles which pass nearby. Here we have a demonstration which uses an analogy. In reality, we are speaking in general relativity of 4 dimensions, 3 spatial dimensions plus time, but here we have only a 2-dimensional demonstration. This is what we can see. So this black flat canvas or surface illustrates a region of a space-time in which there is no mass, no big mass deforming it. And so you can see that particles would move through this region in a straight path. Again, so a straight path. However, if there would be a mass there, then the fabric of a space-time would be deformed by it, pretty much as it is in this case. So here we see, of course, the deformation would depend, the quantity of deformation would depend on how much mass we have. So for example, here we have a shallower potential well, which corresponds to a smaller mass than here. Here we have a much deeper potential well. But in both of them, then, the paths of particles would round. For example, this could be the path of the circular path or elliptical path of a planet next to the sun. And here we would have, for example, the potential that corresponds to a black hole, in which there is much more mass concentrated in a small region of a space-time. So a black hole is a mass so large, concentrated in a radius so small, that actually once particles or light get very close to it, nothing can escape, not even light can escape. So in general relativity, either particles, planets, even light follow as straight a path as they can in a curved space-time. A black hole is so dense, it's a region in which the mass is concentrated in a very, very, very small region, that the gravity attraction becomes so strong close by that not even light can escape. However, for example, the mass of the sun should be concentrated in a radius of 3 kilometers. 3 kilometers is from here to Santa Monica, probably. So the radius should be this small. Instead of the 700,000 kilometers, the mass, the radius of the sun is now. If the mass of the sun would be concentrated in a radius of 3 kilometers, it would become a black hole. The mass of the Earth concentrated in 1 centimeter, in a radius of 1 centimeter, would become a black hole. So it has to become extremely dense. Now let us try to argue the way in which gravity becomes geometry. So free particles follow geodesic paths. These geodesic paths are the shortest paths between 2 points. On a plane, the shortest path between 2 points is a straight line. But on Earth, for example, if you can follow the path of planes that try to move in the straightest path possible on Earth between 2 points, this geodesic or straightest path possible, the shortest path between 2 points, are sections of great circles. So assume 2 particles A and B are initially moving parallel to each other on a plane or on a sphere. In the case of the sphere, they are both both thrown northwards, and they keep northwards. Namely, they keep with a velocity which is always parallel to itself. So both A and B keep moving always in a straight path in the same direction. So on a plane, initial parallel paths continue to be parallel. So with a Newtonian gravity, we would say, well, there is no force attracting the two particles, and that's why they continue in a straight path. In general relativity, we would say this is a flat space-time, it's a plane, there is no curvature. Now, on the surface of a sphere, two particles that start always and continue moving north will approach each other. So from the point of view of Newtonian gravity, we would say, well, these particles approach each other because there is an attractive force between the two. From the point of general relativity, would say, well, the fact that the path of these particles approach each other is due to the curvature of the sphere. Now, we have talked about applications that are far removed from our lives. For example, gravitational lensing. But you could say, well, does general relativity affect my everyday life in any ways? And yes, it does. And for this, we have to understand the following effect. We are going to use again the principle of equivalence. So this is the equivalence between what would happen in an accelerated spaceship in the middle of nowhere where we can neglect gravity, and what would happen if this spaceship would be on Earth, just standing still on Earth. So let us consider two observers, A and B, one on top and the second at the bottom of this spaceship. This spaceship is accelerating upwards. The clock A throws pulses of light at regular intervals, for example, 1 second. So 1 second, one pulse, another pulse, another pulse. Because the velocity of the point at which of reception where B is always moving faster with respect to where A was when it was at the time it was emitted. So the velocity of B is always faster than the velocity of A at the point of emission, right? It takes a short time for the light to travel from A to B. In this time, the vessel has moved. So essentially, the next light pulse from A to B must go always less distance as the velocity is greater. So the pulses travel less and less distance, so they arrive faster. So the intervals at which B sees the rays of the pulses, the rays of light emitted by A, is shorter. So B sees the A clock as running fast. So the same thing applied on Earth. Clocks that are higher up with respect to Earth run faster. Now you can say, well, is this important for anything? This is very important for the global positioning system. So we have seen already in our special relativity class, global positioning system consists of a network of satellites that tell the position and time at regular intervals. So they say, at this time, I'm in this position. At this time, I'm in this position. Your global positioning system in your hand, in your car, receives these signals and then can figure out what's the position of the receiver. Now, the precision that we want from a GPS location is about 1 meter. So from that, we know the precision we need in time, knowing in how long light travels a distance of 1 meter, because the signals that are coming from the satellites travel at the velocity of light. So the distance of 1 meter divided by the speed of light, which is 300,000 kilometers per second, is 3 nanoseconds. 1 nanosecond is 1/1,000 million of a second. So this is the precision needed in time. Now, because the clocks on board of these satellites are moving faster, there is a special relativistic effect. Moving clocks run slower. So this is time dilation. And so it would, if not corrected for the special relativity effect due to the velocity, the clocks would accumulate 7 microseconds per day. A microsecond is 1/1,000,000 of a second. That means it's a rather large error with respect to a microsecond. Now we can add also the general relativistic effect. Because the satellites are higher up, they are at an orbital distance of 20,000 kilometers. Then they run faster, and this is a general relativistic effect. So in a day, without correcting for general relativity, we would have an error of plus 45 microseconds. And the special relativity due to the time dilation of moving clocks would get a correction of 7. They have opposite signs. This 38 microseconds per day cumulative error would translate in a day in an error in the position that would be 11 kilometers per day. So without the general relativistic and special relativistic effects, this would actually invalidate it would turn the GPS useless. Now, again, well, this is very important, but GPS involves satellites. Satellites move at the fastest speed. What about normal speeds? Well, general relativistic effects were measured already in 1971. So Einstein clearly says that time is what is measured by clocks. This is the definition. And so in 1971, Hafele and Keating flew atomic clocks in commercial flights all around the world and proved the relativistic time effects. They measured them, computed them, and the predictions agree with the observation. So this is a modern practical version of the twin paradox. They had two clocks, identical clocks, synchronized. One stayed put, stayed on Earth. The other went in a trip and came back. But in this case, the velocity is just the velocity of commercial airplanes instead of relativistic speeds. But this is a version of the twin paradox. So nowadays, we can do much better. And in 2010, one can measure, and here you can see the reference, Chu et al. In Science, 2010. Gravitational time dilation we can see at the scale of daily life. So here we can see the difference. This is the difference in frequency. So this proves that actually clocks run faster when raised a certain amount, when elevated by a certain amount. In this case, here in the change, when the change of rate in the clock happened, was measured, a clock was elevated by half a meter. So half a meter is about a third of your height. And so now in 2010, we can measure gravitational time dilation when something is moved just by half a meter. So we can see that relativity, the theory of relativity, is not any longer a theory about strange, far away, inaccessible objects, but actually it is something that we have to deal with in our everyday life.